Let's take a look at section 3.3, division of polynomials. So whenever you divide out by a polynomial, one way we've done it in the past has been using long division. For those of you who don't remember long division of polynomials, let's go ahead and take a look at that now to remind ourselves of how this works. So the long division algorithm works the same for polynomials as it does for regular numbers. So remember how we divide just regular set of numbers using long division. We can say something like, what is 372 divided by 5? All right. We can set this up by taking 372. We're going to divide by the number 5. Now, when we divide, we don't divide the entire number all at once. We start from the front and work our way to the back. So we don't say 5 goes into 372. We say, well, 5 goes into 37, something simpler, a smaller part. 3 goes into 37 7 times. And once you know that number, 7 times 5 is 35. We subtract, and that gives us 2. But we're not done yet. We take the next number, we bring that down, and then divide again. 5 goes into 22 4 times. And now once you have this number, 4 times 5 gives you 20. And when we subtract, we end up with a remainder of 2. So our answer is 74 with a remainder. There's a couple ways you can write that. Of course, one way is to write that as 74 with a remainder of 2. However, we can write this as a mixed number by saying that's 74 and 2 over 5. This gives you your whole number. That's the numerator of your fraction, and the original divisor is your denominator. Dividing polynomials works exactly the same way. So let's say, for example, we have 3x squared plus 7x plus 2, and we're dividing that by, let's say, x plus 5. This works the same way. You take your numerator, 3x squared plus 7x plus 2, and we're going to divide that by x plus 5. Now, we don't do the whole thing at once. You start from the front, and we say, okay, x plus 5 goes in here. Now, you'll notice that's still a little complicated. We can do a little bit better by looking at just the very fronts of each of these polynomials. So here we say, okay, let's take just the 3x squared and divide it by just the x. Oh, well, now that's a little bit simpler. 3x squared divided by x is just 3x. So I'll write that right here. Now, once I know what's up here, this times this goes down here, just like we had over here. 7 times 5 is 35. Here, 3x times x plus 5 is 3x squared. 3x times 5 would be 15x. And then once we get here, we're going to subtract. So we subtract. Remember, we're subtracting the entire thing. So it's not just minus this one. It's also minus this one. So let's do our subtraction. 3x squared minus 3x squared. Well, that's 0. That's gone. I'm going to go ahead and cross that out because that's been subtracted away to 0. If I take 7x minus 15x, that's going to give me negative 8x. But I'm not done yet. I can bring down the next number. So now I do it again. I look at just the fronts, and I say, okay, negative 8x divided by x, well, that's just negative 8. So I put my negative 8 up here. And now, just like before, 4 times 5 up here gives me 20. I do the same thing over here. 8 times x plus 5, well, that'll give me negative 8x minus 40. And now if I take those and subtract the entire line away, I end up with, well, let's see, those go away. A number minus itself is 0. And now double negative makes that a positive, so be careful with that. 2 plus 40 gives me 42. Now I can write down my answer. And again, one thing I could do is I could write this as my whole number and a remainder. But the way we're going to want to do it for our purposes is going to be this second way, like a mixed number. This right here is like your whole number. It's the main part of your answer. This remainder will be the numerator of your fraction. And the original divisor, the thing you originally divided by, that's going to be the denominator. X plus 5. Just like that. Okay? If ever you have a polynomial that you're dividing by that doesn't have these in order or that's missing some terms, you need to make sure you fill those in. So let's say we have 2x minus 5 plus x to the third divided by x minus 2, like this. You wouldn't divide this out this way. First, what we want to do is we want to rewrite this in descending order. Same thing for the denominator. If there's ever a case when the denominator is not in descending order, we want to start with the biggest power down to the smallest. So here, before I do anything else, I'm going to rewrite this as x to the third plus 2x minus 5 over x minus 2. Now, when you write it this way, you realize that one of your terms is skipped over. We have a power 3, a power 1, and a power 0. But you're missing a power 2. Right? So that's called a missing term. And whenever you have a missing term, what we want to do is want to fill it in by writing it as that term with a coefficient of 0. So in other words, since we're missing x squared, that means there's no x squared. So we're going to write that literally as writing no x squared. Everything else we leave alone, like that. So now, that's what we're dividing. It's not that there's anything wrong with these. It's just it'll be simpler and it'll follow our pattern better if we write it this way. So right now, you should pause your video and give this a try. Actually, take your numerator divided by your denominator and see what you get. Once you're done, unpause the video and I'll walk you through it. So give it a try. All right, so I'll assume you've already paused. You've taken a few minutes to give this a try. And now let's go through and see what it looks like. So just like before, you're going to take your numerator. So that'll be x to the third plus 0x squared plus 2x minus 5. All right, we don't try to use this one. We go ahead and go with this one. And we're going to divide that by x minus 2. So that's your setup. Now when you divide, you start from the front, working toward the back. So we ignore everything but these terms. And here we say, okay, x to the third divided by x, well, that gives us x squared. So let's go ahead and write that right here. That's going to give me x squared. And now this times this goes in here. X squared times x is x to the third. And x squared times minus 2 is minus 2x squared. Just like that. Now, if I subtract those away, we got to be careful with the double negative. Minus a minus makes that a plus. So here this goes away, and we're left with 0 plus 2x squared, which is 2x squared. And we bring down the next number. All right. We do it again. Here, looking at just the fronts, I say 2x squared divided by x. Well, that's just going to give me 2x. So I'm going to write that up here. I'm going to write that as plus 2x. And now I multiply. 2x times x will give me 2x squared. 2x times negative 2 will give me negative 4x. And then I can subtract those two lines from each other. If I take 2x squared minus 2x squared, well, that's 0. That's gone. Notice every time these go away. That's one way of checking to make sure you're doing that right. 2x minus a negative 4x, well, that'll give me 6x. Double negative makes that a plus. And now I can bring down my last term. So now I do it one more time. If I take 6x and divide it by x, that's going to give me just the number 6, which I can go ahead and put up here. So I'll say plus 6. And now 6 times x minus 2 will give me 6x minus 12. And if I subtract those two lines away from each other, I have 6x minus 6x. Well, that's gone. Double negative makes that a plus. So negative 5 plus 12 is going to give us 7. And now we're done. This answer can be written as x squared plus 2x plus 6 plus, you take your remainder, which is your 7, over your divisor, which is x minus 2. So this is our answer. All right. So now, long division of polynomials is one way we can divide up polynomials. There is a second way that we can do it. Now you might say, well, if there's a second way, why did we bother with this one? This seems complicated. Is the other way simpler? Well, the answer is yes and no. Oh, okay, what does that mean? Well, it is simpler in that it takes a little bit less time and a little bit less writing. Unfortunately, the problem with it doesn't always work. You say, well, doesn't always work, so when does it work? So let's take a look at the next topic in this section. We're going to be looking at a concept called synthetic division. And synthetic division is a way of dividing out polynomials that have a very specific form. So with synthetic division, you do have to be careful. First of all, synthetic division only works if your denominator is of the form x minus a number. So note, this only works if you divide by x minus a number. And here x is a variable, c is just some number here. So this is just some number. You could have x plus a number because, of course, if you have x minus a negative, well, that would give you a positive. So let's take a look and see how that works. In fact, let's go back to one of our previous problems that we saw just a moment ago. Just a moment ago, we saw this right here. We had x to the third plus 0x squared plus 2x minus 5 divided by x minus 2. Let's go ahead and do that exact same division, but using synthetic division as an example. X to the third plus 0x squared plus 2x minus 5, and we're dividing that by x minus 2. That's the problem we just finished doing. Now, for synthetic division to work, we have to make sure that our denominator is of this form, x minus a number, which is exactly what we have. We also have to make sure that our numerators have our terms in descending order, just like before, biggest power down to smallest, and you have to make sure there are no missing terms. If there's a term that's missing, you have to fill it in with a 0. Assuming you have all of that done, the numerator is in descending order, there are no missing terms, and the denominator looks like this, then we can set up our synthetic division to look this way. Take the coefficients of your numerator and write them down in the same order that they appear in the numerator. Not the variables, not the powers, just the coefficients. So here that's going to be 1, 0, leave a little space there, 2, and negative 5. Remember, the negative is part of a number, so if you're writing it down, you write it down along with the negative. And now we're going to divide. We'll put our division box, and that's going to be upside down. Synthetic division looks just slightly different. And now here, we're going to be dividing by the number that we're subtracting away from our denominator. So x minus c, you're dividing by the c. In this case, you're dividing by the 2. Okay? Another way to think about it is you're dividing by whatever number plugged in here makes this 0. All right? So here, this 2, if you plug it in right there, 2 minus 2 would be 0. So that's how you know that's the right number. Okay? So now, for synthetic division, the first step is always exactly the same. In fact, a lot of the steps are exactly the same. You're going to take the first number and drop it straight down. Okay? You don't do anything to it. You don't change it. Just bring it straight down the way it is. If that's a 10, that's a 10. If that's a 2, that's a 2. Here, that's a 1, so we bring down a 1. So now the pattern is multiply on the outsides, add on the insides. 2 times 1 is 2. And now adding these together gives me 2. Multiply these outsides gives me 4. And now add those together gives me 6. multiply on the outside. 6 times 2 is 12. And add those on the inside. 12 plus negative 5 is 7. And that's it. We're done. Now, you'll notice this is just a string of numbers. Well, yeah, but so is this. And this string of numbers represents the coefficients of your polynomial. That's what this will do. This will represent coefficients of your answer. This number on the very end represents your remainder. Every time, this is your remainder. These represent the coefficients of the main part of the polynomial. This last number will always be a constant. This number will always be x to the first power, so 2x to the first. This one will be the coefficient of x to the second power. If there were any more numbers, the next one would be x to the third power, then x to the fourth, x to the fifth, counting up from power 0, power 1, power 2, and on up. So we could write down the answer to our problem. We could write down the answer to this division by saying, okay, that's going to be 1x squared plus 2x plus our constant, which is 6, plus, now that's our remainder, and the way we write our remainder is we write it over our divisor, just like a mixed number, 7 over x minus 2. And that's our answer. And you'll notice that it is the exact same answer to the problem we had before. Of course, it's the same answer. It's the same problem. We've just organized it a little differently. Synthetic division only works in the case that your denominator is x minus 2. If your denominator is something like 5x minus 7, well, then you kind of need long division. If your denominator is something like x to the fifth minus 1, then you definitely need long division. Here, your denominator must be power 1, and it must look of this form, x minus c. Now, there's a little bit of wiggle room with that. And that is, what if you don't have just x minus c? What if it's something like 2x minus c or 3x minus c? What happens if you have an extra number here? There's a little bit of wiggle room. So let's take a look at another example and see how to take care of that. So let's say we have x to the third power plus 6x to the second power minus 5x plus 1. Okay? And we're going to divide that by, let's say 2x minus 1. Okay? Now, you'll notice that this denominator doesn't work. It doesn't fit this pattern. The numerator is fine. It's a polynomial. It's in descending order, and I'm not missing any terms. But my denominator is supposed to look like x minus a number. And it doesn't. It looks like 2x minus a number. Well, that's fine. There's a little bit of wiggle room on this. Because what I can do is I can say, okay, that's x to the third plus 6x squared plus 5x plus 1 divided by 2 times x minus a half. Notice all I did was I said, okay, look, let me take that 2 right here and factor it out of these two numbers. If I multiply this together, 2 times x is still 2x. 2 times negative a half is still negative 1. So that's all fine. So if that number wasn't there, everything would be good. I would just be able to divide by this using synthetic division. Oh, okay, well then let me get rid of that number. So how do you get rid of that number? Oh, well, just divide it out. So here, let me rewrite this as, okay, well that coefficient is 1. So let me write that as 1/2 x to the third. Here, this coefficient is 6, but I'm trying to divide out by 2. So that'll be 3x squared. That coefficient is 5, but again, I'm trying to divide away the number 2. So I can make that 5 halves x. And I have 1 over 2, which is, well, 1/2. And that's being divided by x minus a half. So notice now this fits the correct pattern. I have a numerator that has a set of coefficients. The numerator is in descending order. And my denominator now looks like x minus a number. All right, so now I can use synthetic division. You might look at that and say, well, those are fractions. Yeah, well, sometimes we deal with fractions. So let's go ahead and set that up. We're going to have 1/2, 3, 5/2, 1/2, and we're dividing synthetically by the number that was subtracted from x, or if you prefer, you can think of it as what number goes in here to make that 0. All right? So, my apologies, that should be a minus right here. that should be a minus right here. So that 5/2 should be a minus 5/2. We're dividing this whole thing by 1/2. All right. So now we perform the same pattern. We're going to take our 1/2 and drop it straight down. And now multiply on the outsides, add on the insides. It's a little more annoying because of the arithmetic involving fractions, but it doesn't change how this works. So 1/2 times 1/2, well, that's 1/4. And if I take 1/4 plus 3, that's going to give me 13/4. Let me write a little bit bigger here, 13/4. Now, if I multiply 13/4 times 1/2, I get 13/8. And if I add those together, well, let's see. If I have 5/2, that's a negative, plus 13/8. Remember, you need a common denominator to add fractions. So here I can multiply this top and bottom by 4. And now I have a set of fractions that reads negative 20/8 plus 13/8, which gives me 20. Negative 20 plus 13 is negative 7/8. So that's what I get if I multiply, or if I add together negative 5/2 and 13/8. I get negative 7/8. So let's put that right here, negative 7/8. And now if I multiply these together, 1/2 times negative 7/8 is negative 7/14. Oh, sorry, negative 7/16. And now I can go ahead and combine these. That's going to be 1/2 minus 7/16. Looks like that. Again, giving these a common denominator. Well, I can multiply the top and bottom by 8. And that'll give me 8/16 minus 7/16, which is just 1/16. Like that. So now, 1/2 minus 7/16 is 1/16. And now I'm done. In spite of the fact that the numbers are slightly less amenable, a little less friendly, this still works out the same way. This is our remainder. This is our constant, x to the first power, x to the second power. So we can write out our answer as 1/2 x squared, 1/2 x squared, plus 13/4 times x minus 7/8. And then we have our remainder over our divisor, over our x minus 1/2. Here, you could write this a little bit simpler. We can write that this part right here, let me just go ahead and take this part off to the side on its own. If I have 1/16 divided by x minus 1/2, remember, dividing by a number is the same as multiplying by its reciprocal. So this is the same as saying 1/16 times, instead of saying I'm dividing by this, I'm going to say I'm going to multiply by 1/this. Like that. But now 1 times 1 is 1. 16 times x and 16 times 1/2. Let's see, that's 16x. And then 16 times negative 1/2 is negative 8. So if you like, you can always combine those as 1/2 x squared plus 13/4 x minus 7/8 plus 1/16x minus 8. And that'll happen whenever you have a fraction here, and that'll happen whenever you have a fraction over here, just like that. And that would be our final result. So now, you should go ahead and try one. Go ahead and give this a try. Take 2x to the fourth power minus 3x squared plus 5x minus 1. And you're going to divide that synthetically by x plus, let's say x plus 2. Now here, notice, you do have a missing term. And notice here, this is x plus a number, not x minus a number. But of course, you can always write plus as minus a minus. All right? So you could always write this as x minus a negative 2. So give this a try. Pause the video for a minute, do the synthetic division, and when you think you got it, come back and see what happens. All right, so let's go through it. Our denominator can be written as x minus a number, right? X plus 2 is the same as x minus a negative 2, so we're fine there. Don't forget, your numerator should not have any missing terms, so we need to fill those in. That's going to be 2x to the fourth plus 0x to the third. Right? There was no x to the third, so we fill it in as a 0. Minus 3x squared plus 5x minus 1. So this is a little bit longer than the examples we've seen before. We don't have any fractions, though, so the numbers shouldn't be too bad. So let's go ahead and divide out. So take your coefficients of your numerator and write them in the order that they appear from our polynomial in our numerator, in descending order. So let's see, that's going to be 2, 0, minus 3, 5, and minus 1. And now we're going to divide synthetically by, and here, the number we're subtracting is negative 2. Or, if you prefer, you can think of that as negative 2 is the number that I would plug in to make this 0. Negative 2 plus 2 would make that 0. So, you drop your 2. Negative 2 times 2 is negative 4. Now add those together to give you negative 4. Negative 2 times negative 4 is positive 8. Add those together to give you 5. 8 minus 3 is 5. Yeah. Negative 2 times 5 is negative 10. And if you add those together, you get negative 5. And now negative 2 times negative 5 is positive 10. And if you add those together, negative 1 plus 10, that'll give you 9. And now we have this as our remainder. And we can write out our answer. So this would be x to the first, this would be a constant, first power, second power. Here we have something that goes all the way up to third power. So here we would write our answer as 2x to the third power minus 4x to the second power plus 5x to the first power minus 5. And then we have our remainder over our divisor, over our x plus 2. Or you could write it as x minus a negative 2, but since we're done with the division, you could just write it back in the original form. Okay? And that's our answer. Now you may notice about synthetic division that it is simpler than long division. It's a little shorter, takes less space to write, and there's a lot less going on. You still get the right answer though. On the other hand, you'll notice that it is a bit more limited. For long division, you can make your denominator anything you want. For synthetic division, it has to look exactly like x minus a number. So this is not quite as useful as long division. However, given what we're going to do in this section and in the coming sections of chapter 3, it does help us significantly. Because even though it is limited to denominators that look like this, the denominators, the polynomials that we're going to be dealing with, most of them will look like this to begin with. So even though this is a shortcut to long division that's somewhat limited, it is limited in a way that we can still use it. So now let's take a look at something a little different. Let's take a look at a theorem. A what now? A theorem. Well, that sounds hard. I don't know what a theorem is. Well, let's see here. A theorem can be thought of as a promise, a mathematical promise. A theorem says, if certain conditions are true, if you know that this is true, then I guarantee you that without exception, this other thing will also be true. It's different from a formula. A formula says if you have these numbers, you can plug them in here and get an answer. A theorem rather connects one result to another result, or one idea to another idea. So let's go over one of our very first theorems that we see. Up to now, the only theorem you're probably familiar with is the Pythagorean theorem. But here, let's go into what's called the remainder theorem. It reads the following. Let f of x be a polynomial function. Okay? That's the condition. Whenever you have a theorem, there are some conditions that must be met. If this first condition is not met, then the theorem doesn't apply. So if, for example, f of x is not a polynomial function, if it's a rational function or a radical function, then none of this applies. That's what I mean by a promise. If you fulfill this part of the promise, math will fulfill this part of the promise, right? So let's say f is a polynomial function. Okay, so if that's true, what happens? All right, if f of x gets divided by x minus c, if that has a remainder, we're going to call that remainder r for remainder, then f of c equals to r. Now that sounds a little strange. What this is saying is, if I give you a polynomial function, if I divide it by x minus c, the remainder is the same as if I had just plugged in the number c into the function to begin with. Now, whenever you have a theorem in math, it's a promise. But of course, promises can be broken, promises can be misleading, so we don't usually accept them at face value. Anytime you have a theorem, you accompany it with a proof. A proof is a way of formally confirming that this does in fact lead to this. In other words, it's a way of showing that if my conditions are met, I have no choice but for the second part to be true. Some of our theorems in algebra, in fact, a lot of our theorems in algebra, are a little long and too complicated for a freshman level algebra course. So you'll see that several of our theorems, I'm going to just state the theorem and then leave it at that, because we wouldn't have the time or ability to go through the full proof. However, this one is a nice example to start with because its proof is nice and accessible to us. It's not something that we would take a very long time to do, and it is something that should be understandable if you take a few minutes to try to think about it. So let's go through it here. All right, so let's start off with our conditions. So let's say f is a polynomial function. So let f of x be a polynomial function. Okay, well, since it's a polynomial function, that means I can use synthetic division to divide it by x minus c. So I can use synthetic division to divide by x minus c. Okay, and when I divide by x minus c, the way my answers usually look, I get something that looks like this. I get something that is, I have a polynomial plus my remainder over my divisor. This is just one of our examples from earlier. So if I divide, my answer will be a polynomial plus remainder over divisor. Okay, so if I take f of x and I divide it by x minus c, my answer will be some polynomial. Now, I don't know what that polynomial is, and it's going to turn out not to really matter, so I'm just going to give it a name. I'm going to call it g of x. What does matter is that once I have that main part of my polynomial written, the last part is my remainder over my divisor, over the exact same thing that I had over here. Okay? So if I take a polynomial function and I divide, I get some polynomial plus my remainder over my divisor. Now, notice that if I take x minus c, I can multiply it across both sides. So here, let me rewrite that line so I give myself a little more space. I'm going to write this as f of x over x minus c, because after all, that's what it means to divide. I'm putting it over that. And that's equal to g of x plus r of x minus c. So now what I'm going to do is I'm going to multiply across by x minus c. After all, x minus c, that's just some number. And if I'm going to change one side of my equation, I can do the same thing to the other side of the equation, and everything is still perfectly valid. Right? So as long as I multiply on both sides of my equation by x minus c, then everything's still valid. My equation's still true. But now if I multiply those, hey look, this divides into this. And likewise here, this divides into this. So it must be true that the function f of x, and that's not by itself, is equal to g of x times x minus c plus some number r. Okay. Now remember what our theorem says. Our theorem says something about f of c. Our theorem has something to do with what happens if I plug c into my function. Well, look, here's my function. F of x equals to all this stuff. So let's see what happens when we plug in c. Thinking back to a previous chapter, the way function notation works, if I have this x, that's my argument. It represents all of these x's. So if I replace that x with a c, well, then I can replace all of these with the value of c. So now, g of c, well, that's a number. Right? I plug the number c into a function. Okay, that gives me some number, and I don't know what it is. But it turns out not to matter what this number is, because this is the important part. Notice here, c minus c. Well, c minus c is 0. And this is 0 times something. Well, 0 times anything must be 0. So here, this whole thing must equal to 0. That's gone. So now f of c is left by itself, and that's going to equal to, well, if that's gone, I'm left with just r. But that's what I wanted. If f of x is divided by x minus c, well, that's what I did. I took f of x and divided it by x minus c, and I had my remainder was r. If that's the case, then if I take c and plug it in for my f, that's going to give me just the remainder r. So that concludes my proof. At the end of a proof, we'll put a little box here to signify the fact that, okay, that's the end of our proof. That's what we wanted. And now this confirms that our theorem is true. Once you have a theorem that's been proven, you can now use it without ever having to worry, well, maybe it doesn't work. Because here, this shows that it has to work. If, as long as you have a polynomial function that you're dividing by something like x minus c, it forces this to be true. So now let's take a look at an example of what this theorem says, and it actually is a nice kind of computational shortcut. So let's continue over here. So let's say we have a function, and we'll give it a name. We'll call it g. So let's say we have a function g of x, and that's going to equal to 3x to the fourth power minus 22x to the third power plus 51x to the second power minus 42x plus 8. Okay? And now the question is a very simple one. The question is, let's go ahead and find g of minus 1. Now, of course, one thing you could do is you could go through and plug in minus 1 for all your values of x. 1 right there, negative 1, negative 1, negative 1. And then you could go through and perform the arithmetic. Now, that's not difficult to do, but it does take a bit of time. After all, you're raising something to a power, then you're doing a multiplication, then a raising to a power, another multiplication, power, multiplication, multiplication, and then you're doing all these additions and subtractions. You note that that could get even harder if this number is a fraction, a decimal, or just a big whole number. So here we're going to use the results of our theorem, which say, well, look, the answer to this is the same as if I were to take my polynomial and divide by x minus that number. So here, by our theorem, g of minus 1 is equal to the remainder, is equal to the remainder of g of x divided by x minus the number I'm trying to plug in. Notice that's a negative, so that would be minus a minus 1. Or in other words, it would be equal to the remainder of g of x over x plus 1. So let's do that. Let's go ahead and find. So we want the remainder of g of x over x plus 1. Right? Minus a minus means that's plus. All right. So we don't care about the entire answer. We just care about the remainder. So let's go ahead and do that. Synthetic division works by taking the coefficients here, 3 minus 22, 51, negative 42, and 8. And now we're going to divide by the number that we subtracted over here. Or if you prefer, we're dividing by the number that we plug in here to make this 0. Either way, you're using negative 1. All right, so let's go ahead and do that. Take your first number, drop it down. And now we say multiply. Multiply the outsides, add the insides. Negative 1 times 3 is negative 3. Add these together is negative 25. Multiply these together. That's going to give me positive 25. And add these together gives me 76. 76 times negative 1 is negative 76. And add these together, since they're both negative, that'll give me a negative 118. And if I have a negative of a negative, that'll give me a positive. So that's positive 118. And then if I add these together, that'll give me 126. Okay. And so that means that if, so that's my remainder. If I were to come over here and say, what is g of negative 1? Oh, it must be 126. That's equal to 126. Just like that. Here, let's have you try one. In fact, let's use the same function. So let me just write that one down again. We're going to take g of x is equal to 3x to the 4th power minus 22x to the 3rd power plus 51x squared minus 42x plus 8. Okay. And the question, let's just say find g of 2. So find g of 2. Okay. So you could take the number 2 and plug it in, but that would require a whole lot of arithmetic. Take 2 to the 4th times 3, and then 2 to the 3rd times negative 22, and then 2 to the 2nd times 51, and then negative 42 times 2, and then add all those along with the 8. What we would rather do is we're going to use our theorem. So give that a try. Pause the video for a minute and use synthetic division to try to find g of 2. Once you think you've got it, unpause the video and we'll walk through it. All right, so let's go ahead and give this a try. We have 3 minus 22, 51, negative 42, and 8. Those are the coefficients of our numerator. And now we're dividing synthetically by the number we're trying to plug in. All right, here we're trying to plug in the number 2, so we're dividing synthetically by the number 2. Just like in the previous example, we were trying to plug in the number negative 1, and we're dividing synthetically by negative 1. So let's give this a try. Take your 3, bring it down. All right, so now we don't care about these numbers, just the remainder. 2 times 3 will give me 6. And now if I add these, that's going to give me negative 16. Multiply these, gives me negative 32. And if I add these, I get 19. Multiply this by 2, gives me 38. And if I add those, gives me negative 4. And 2 times negative 4 is negative 8. And if I add those, I get 0. And since that's my remainder, that must be my answer. So notice I never had to worry about a power. I never had to worry about any multiplying by the coefficients or any of these additions or subtractions. Just a synthetic division, this result gives me my answer. So g of 2, if I were to take the number 2 and plug it in there, raised to a power, multiply, subtract, all the way across, I would get 0. and that's my answer. Okay? Note a couple of things. One, this is a little shorter than plugging in the number most of the time. In some cases, it'll be significantly shorter. The other thing to note is that right now, we found a number that if we plug it into the function g, makes the function 0. But that was something that we were looking for in previous sections. We were looking for the zeros of a polynomial function. We were looking for numbers that make the function 0, because that's where our x-intercepts are going to be. So in coming sections, we're going to be using this synthetic division technique to try to find what numbers, when plugged in, make this 0, and synthetic division will help us confirm which ones are correct. This brings us to what we call the factor theorem. So here's another theorem that we're going to be looking at. And here the theorem says the following. So the name of it is the factor theorem. If we refer to the factor theorem, that's what we're talking about. And it says, all right, let f of x be a polynomial function. That's all you really require. If this is not polynomial, this doesn't work. But as long as you have a polynomial function, the following two things must be true. If f of c is equal to 0, then x minus c is a factor of f of x. The other way around is also true. If x minus c is a factor of f of x, then f of c must equal to 0. This can be used to help us factor polynomial functions that otherwise could not be factored. In previous sections, we've seen that factoring polynomial functions is something that's useful to us, so let's take a look at an example of how that would work. Consider this following polynomial: 3x to the third plus 16x squared minus 5x minus 50. And the question is to factor that. Now, you could try to factor that in using the techniques that you know. You might notice that it has the polynomial with 4 terms, so you might try to factor by grouping. But if you try it, you quickly realize that it doesn't work. You look for a common factor and you realize it doesn't have any. It's not the sum of cubes or the difference of cubes. It's not the difference of squares. AC method doesn't work on this because it's not a quadratic. You can't really do anything to it. None of the factoring techniques that you know work on this polynomial. But we're also given one extra little piece of information. Now, for right now, that's just given. That fell out of the sky and you it's true. In later sections, we'll show you how to find that one yourself. But for now, it's something that we give you and you take it for granted. So the piece of information that you've been given is f of negative 2 is equal to 0. That doesn't sound like a lot, but that little bit of information is enough to have you factor this entire polynomial. So let's see how that works. Notice that our factor theorem says if f of c is equal to 0, then x minus c is a factor. All right, well, here we have f of minus 2 is equal to 0, so that's my c. So x minus that number, x minus c, must be a factor. So all this does is it tells me that, if f of negative 2 is equal to 0, that means x minus a negative 2, which is the same as x plus 2, is a factor. You say, okay, well, you have one factor of your polynomial, but what about the rest? I mean, that's a third-degree polynomial function. Here you have a first-degree polynomial function. Something's missing, obviously. Well, let's see. We know from the beginning of the section that if we have something that looks like this, x minus a number, x minus c, we can divide synthetically to divide out the expression from our polynomial. So let's do that. Let's take our polynomial that we're trying to factor, take 3, 16, negative 5, and negative 50, and we're going to divide synthetically by the number that was subtracted from x, or by whatever number makes this equal to 0. Either one's fine, because you both get the same number. So let's go ahead and drop our 3 and start multiplying on the outsides and adding on the insides. Negative 2 times 3 is negative 6. Add those together gives you 10. Negative 2 times 10 is negative 20. Add those together gives you negative 25. Negative 25 times negative 2 is positive 50. Add those together gives you 0. Now, note that your remainder is equal to 0. You already knew that, though. You already knew that plugging in negative 2 would give you 0. So you knew that the remainder should be 0. That's not the part that's interesting, though. This other expression is a polynomial without a remainder. What that means is, if I take 3x to the third plus 16x squared minus 5x minus 50, that was my original polynomial. If I divide that by x plus 2, which is what I did here by using synthetic division, I'm going to end up with this polynomial, 3x squared plus 10x minus 25. But notice, if I multiply on both sides by this denominator, x plus 2 and x plus 2, these divide away, these two divide away, and now I'm left with this polynomial times this polynomial equals to that polynomial. But that's what factoring is. Factoring is trying to take the original polynomial and writing it as the product of two other polynomials. So by knowing that that one number makes the function equal to 0, that tells you that this is a factor, and by dividing by that factor, that gives you your other factor. So here we're left with 3x to the third plus 16x squared minus 5x minus 50 is equal to x plus 2, that's the factor that we got out of the factor theorem, and 3x squared plus 10x minus 25, that's the factor that we get after synthetic division. But notice now that's a quadratic. And quadratics we can factor nice and simply. We could use the AC method. We could use the quadratic formula for this even. So let's go ahead and give that a try. Let's factor that out. So here I'm focused on just this part. That's already as factored as it's going to get. It's linear. It's got coefficient of 1, lead coefficient of 1. Here I'm just going to look at this part. I can go ahead and factor that out because if I know the zeros of that polynomial, that means I know its factors. Again, that's what the factor theorem says. If I know the zeros, then I know the factors. But I know how to find the zeros of quadratic polynomials very easily. I can use the quadratic formula. So here, let's see what that looks like. The zeros of 3x squared plus 10x minus 25 are given by x is equal to negative b, right, negative b, plus or minus the square root of b squared minus 4 times a times c, all divided by double the value of a. All right, let's simplify that. My denominator, 2 times 3 is just going to give me 6. Inside my radical, 10 squared is 100. Here, this double negative makes that a positive. So I have a positive. 4 times 3 is 12, times 25 is 300. So that's plus 300. That's going to give me negative 10 plus or minus the square root of 400, all over 6. Now, 400 is a squared number. If I take the square root of 400, I just get 20. So this will give me negative 10 plus or minus 20 over 6, just like that. And now from here, I can get my results. Because after all, those are just two regular numbers. I can go ahead and subtract or add and divide out. This is negative 10 plus 20 over 6. And it's also negative 10 minus 20 over 6. All right, that's what plus or minus means, plus or minus. 20 minus 10 is 10, divided by 6. Well, that's 10 over 6, which I can rewrite as 5 over 3. So that's one of the zeros of that quadratic. Here, negative 10 minus 20 is negative 30. Negative 30 divided by 6 is equal to negative 5. So I have the two zeros of my quadratic, which means I can use those to factor out my quadratic factor. So let's come over here. We can write that as, and here I'm just going to write down the original polynomial, which was 3x to the third power plus 16x squared minus 5x minus 50. And we learned that that was equal to 3x squared plus 10x minus 25 times x plus 2. But then we saw that this had negative 5 and positive 5/3 as zeros. Well, remember what your factor theorem says. It says if you have a 0, then x minus that 0 is a factor of your function. So here, I can say, well, if I know that negative 5 is a 0 of this, then x plus 5 must be a factor. If I know that 5/3 is a 0 of this, then x minus 5/3 must be a factor. I have my zeros from before. All the way down at the bottom, we got that 5/3 and negative 5 were zeros. So if negative 5 is a 0, that means x plus 5 is a factor. Because if you plug that in there, that would be 0. Same thing here. If 5/3 is a 0, then x minus 5/3 is a factor. Because plugging that in there would make that 0. Here, that x plus 2, I'm not going to do anything to that. Let's leave that alone. And now you'll notice something is missing, something's wrong here. Because all of a sudden that 3 went away. Well, it didn't really go away. All we did was we factored it out. Because notice here, this x stays that x. Here, x times x is x squared. Well, yeah, but it should be 3x squared. What happened to the 3? Nothing. We factored it out. When you use the quadratic formula, what you're going to get is you're going to assume that your coefficient is factored out at the very beginning. So here, if that's the number 3, then the number 3 is our leading coefficient, which gets factored out. If this had been a 9, we'd put a 9 there. If that had been a 7, we'd put a 7 there. And there we go. That is a fully factored polynomial. And we get all of that just by knowing 1 0 of our function. So let's have you give this a try. The question is factor x to the third plus 4x squared plus x minus 6. And here we're going to give you something. We're going to give you that f of, let's say f of negative 3 is equal to 0. All right? So you should pause the video now and give it a try. Once you think you've got the answer, go ahead and unpause and we'll walk through it together. All right, so let's go ahead and give this a try. Given that f of minus 3 is equal to 0, that's another way of saying that x minus a negative 3, which is the same as saying x plus 3, is a factor. Okay, so we have a factor of our polynomial function. So now once you have one factor, you can find the remaining factor through synthetic division. So let's go ahead and give that a try. We have 1, 4, 1, and minus 6. And we're going to divide synthetically by the 0 that we know for our function. So we're dividing by negative 3. We drop our 1. Negative 3 times 1 is negative 3. And if you add those, you get 1. Negative 3 times 1 is negative 3. And if you add those, you get negative 2. Negative 3 times negative 2 is positive 6. And if you add those, you get 0. But you already knew that. You knew your remainder was supposed to be 0. That's not the important part. The important part is that this is the remaining factor of our polynomial. So now we can write this as x to the third plus 4x squared plus x minus 6 is equal to, well, we already knew that x plus 3 is a factor. Right? We were given that at the very beginning. F of minus 3 is equal to 0, which means x plus 3 must be a factor. And our other factor is the one that we just got through our division. That's going to be x squared plus x minus 2. And we can factor this out even further. This one, we could use the quadratic formula like we did in the previous example, but notice that that's kind of overkill because that one can be factored much more quickly and much more simply in the traditional method. Namely, what two numbers can be multiplied to give you negative 2, but add up to give you negative 1? What two numbers can be multiplied together to give you negative 2 and add up to give you positive 1? Well, that's going to be 2 and negative 1. 2 and negative 1. 2 times negative 1 is negative 2. Meanwhile, 2 plus negative 1 is positive 1. So that means that this x squared plus x minus 2 would factor as x plus 2 and x minus 1. And there we go. That polynomial is now completely factored. And even though we couldn't do this by any of our previous techniques, we couldn't use any basic factoring on this starting polynomial, just knowing the fact that negative 3 is a 0 of our function is sufficient to factor that out. And again, for now, this is something that's given to you. In later sections, we'll show you how to find that yourself. Finally, the last thing we're going to do for this section is we're going to look at a problem that's kind of like what we just saw, but backwards. Instead of taking a polynomial function that's given and factoring it out, we're given some information about the factored polynomial and asked to recreate it from scratch. So a problem would read something like, write a polynomial function and here we're going to call it f of x, which is of degree, let's say of degree 5, and which has zeros 2, 5 halves, which has 2, 5 halves as zeros of multiplicity 1, and which has 0 of multiplicity 3. All right, so we're using the factor theorem again, which says, okay, if I have this as a 0, then I know for a fact that x minus that number must be a factor. All right. Now, if x equals to 5 over 2 is a 0, then that means that x minus 5 over 2 must be a factor as well. We're just using the factor theorem. Now notice these are zeros of multiplicity 1. Thinking back to a previous section, the multiplicity is the power of the factor that that 0 comes from. So here, this 0 comes from this factor, and since that has a multiplicity of 1, that means this factor has a power of 1. Same thing here. This 0 comes from this factor, and since it has a multiplicity of 1, that makes that factor have a power of 1. Finally, you have 0 is a 0 of our function. So x minus 0 is another factor, x minus that number. But now the multiplicity is 3, which means this factor will have a power of 3. Notice x minus 0, you don't have to write the minus 0. You can just write that as x. So here we can say f of x is equal to all of this stuff, and we can clean that up ever so slightly by writing f of x is equal to, let me write this one first since it's the simplest one. there's no number here, right? X minus 0 is just x. So let me write that as x. That's got a power of 3, so let me bring that along. And then I have x minus 2, and that's to the first power. And here I have x minus 5 halves, and that's also to the first power, just like that. And there you go. That's a polynomial function of degree 5. After all, the multiplicities add up to the degree, 3, 4, 5. So that does have degree 5. And we could now multiply this all out, but I'm not going to require you to do that. As long as you can get this far, we're perfectly happy. You could, of course, now start multiplying. You could distribute these out, distribute the x to the third, and combine all your like terms. But for the purposes of our class here today, we're going to go ahead and leave that as it is. All right? Notice that this is not necessarily a unique answer, meaning there are other answers that could also satisfy this polynomial function. For example, if I felt like it, I could come over here and just double everything, times 2. And I still would have 0 with a multiplicity of 3. I would have 2 as a 0 with multiplicity 1. I would have 5 halves as a 0 of multiplicity 1. And that 2 would change the function, but it wouldn't change anything about the zeros of the function because the factors all remain the same. So here, that 2, I could change it to an 8 if I wanted to. And again, it changes the function, but it doesn't change anything about the zeros or their multiplicities. So if you're working with someone else, or if you're looking in the back of the book, or if you're trying to find what the answer is and you see my function looks a little different from theirs, that's okay. There's different versions of this answer. These are not unique polynomials. That's why the question is write a polynomial function. There's going to be more than one. Here I'm going to use just the simplest version. I'm not going to put any number there at all, but hypothetically you could, and it would still be perfectly fine. All right, so that is it for our section 3.3, division of polynomials, the remainder and the factor theorems. And if you have any questions, make sure that you ask during discussion or ask during office hours. And have a nice day.